Lecture on matrix spaces. In last lecture, we introduced the notion of open and closed sets in matrix spaces. Now we begin this lecture with the definition of neighborhood of a point in a matrix space. So we have a definition. Let us consider a matrix space. Let Xt be a matrix space, and then a neighborhood of the point x0 in X is any open ball in Xt with center x0. So a neighborhood of a point x0 in X is just an open ball in the same metric space Xt with center x0. So we have not mentioned here the distance, here the radius of the sphere, radius of the open ball. So radius is any finite real number. Now using this definition, we can define what an open set is. So let Xd be a metric space, then a subset G of metric space, a subset G of a metric space Xt of a metric space Xd is said to be open, is said to be open if given any point x in G, there exists some r positive such that the open ball center at x and radius r is subset of G. That is, i.e., if given any x in X, there exists r positive such that the open ball S centered at X and radius r is contained in G. In other words, if each point of G is the center of some open ball in G, i.e., if each point of G is the center of some open ball, is the center of some open ball contained in G, or equivalently, if every point of the set has a neighborhood contained in the set. This is the alternative definition. Now we are going to prove that in any metric space xt, each open ball is an open set. So we have to remember this definition. So an open set xd in a metric space is any set if each point of that set is center of some open ball which is contained in G. Suppose G is said to be open. Suppose this is our set G. If it is possible that for given any point, say x in G, there x a ball centered at x. So this point x here. So this set G is said to be open if for each point x naught there is some r positive such that this open ball centered at x and radius r, this is contained in G. So then this set is said to be open. Now note that if we look at this point over here, so for this point, if we consider any open ball which is centered at this point, this open ball does not wholly lie in this set G. This is i.e. this is not contained in G. So therefore these points must be excluded from an open set, i.e. the boundary. This is called the boundary of the set. So now what we had to prove is that in any metric space xt, in any metric space xt, each open ball is an open set. So let us prove it. Proof. Let us consider an open ball centered at x and radius r. Let us consider an open ball as Rx with center x and radius r, which is a positive real number. First of all, observe that this open ball is a non-empty set because x must be there. Observe that SXR is non-empty, so this is not equal to the empty set. This is because since this x is in this open ball. Now what we have to prove? We have to prove this is an open set. So if we take any point, say y in this open ball, then we have to prove any open ball centered at y, that open ball has to be must be contained in this open ball SXR. Now let us take a point. Let y belongs to SXR. So we have this Let us make it more bigger. So this is our SXR. Now this is the center X, so this is the radius R. Now let us take a point here. Say this is point Y. Now if this Y is in SXR, that means so if this Y is in SXR, this implies distance from Y to X is less than R. So distance of Y from X is less than R. Now let us define another real number. Let us take R prime to be equal to this R minus d of xy. Now this is over d of xy. Now R prime is what? R minus d of xi. So this is this distance over here from the boundary to point Y. This is over R prime. Now this whole distance is R. Now if we subtract this R by this distance xy, so we are left with the distance R prime. Certainly R prime will be less than equal to what? R, provided X and Y they may be equal. So it is positive provided X is not equal to Y. Take R prime to be equal to this, such that so this distance over here, this will be positive. Now this may be 0, this distance may be 0 if d of xy is same as R. So in that case, if this y is on this boundary, but that won't happen. So this is positive. Now what we do, we will construct another open ball centered at Y and with radius R prime. Consider the open ball as centered at Y and radius R prime. So this open ball is here. This is centered at, let us take it, so this is point Y over here. This is point Y. So now what we are going to do, we take another open ball centered at Y and radius R prime. That is the open ball, this. Now what we have to prove, we'll show that we will show that we have to prove, in order to prove SXR is open set, we have to prove this open ball is contained in SXR by definition of the open set. We will show that SYR prime, this is contained in SXR prime R. So in order to prove this containment, what we do, we take any point here, and we will show that this point is also here. So consider Z belongs to SYR prime. Now if this is the case, this implies d of YZ, this will be less than R prime. So let us take this point Z over here, this point Z. Now by triangle inequality, we have to, in order to show that this Z is in SXR, we have to show that d of XZ is less than R. That is what we have to prove. Now let us take then we have d of ZX. Now this distance over here, so this distance over here ZX, this will be less or equal to distance of XY plus YZ. So this will be less or equal to distance of Z from X, sorry, Z from Y plus Z from Y and Y from X plus distance of Y from X. Now this is less or equal to, because this d of ZY over here is less than R prime, so this is less than R prime plus distance of YX. Now let us give the value of R prime over here. This is equal to R minus d of XY plus d of YX. So this is equal to R here. So this implies that distance of ZX is less than R. In other words, so this Z over here, this belongs to SXR by definition of this open ball. So now what we have proved, that we have chosen any point in this open ball, and we have proved that any open ball centered at that point is contained in the this open ball XR. Now note that this for this open ball over here, its radius must be less or equal to the radius R. So this proves that any open ball in any open ball is an open set. So we'll prove another theorem over here. Let X be D be a metric space. Then empty set and the whole set X, they are the open sets, are open subsets of, are open sets in XD. Second, arbitrary union of arbitrary union of open sets is an open set. Third, finite intersection of open sets is an open set. Proof of first. Now the empty set is open because there is no point in X in empty set which is not the center of an open ball, which is not contained in empty. This sounds weird. Let me make it clear. Since the empty set contains no points, the requirement that each point in empty set is the center of an open ball contained in it is automatically satisfied. So empty set is open. The answer follows trivially. Now the whole space X is open since every open ball centered at any of its points is contained in X. The whole space X is open since every open ball centered at any of its pointers is contained in X.